let us discuss another problem from the chapter Nuclear Physics. The nuclei of a radioactive element A are being produced at a constant rate alpha. The element has a decay constant lambda. At time t is equal to 0, there are n0 nuclei of the element. Calculate the number n of a nuclei of A at time t. The next question is, if alpha is equal to 2 n0 lambda, calculate the number of nuclei of A after one half-life of A and also find the limiting value of n as t tends to infinity. Now if you look at this, the nuclei of a radioactive element A are being produced at a constant rate alpha. For example, if this is the nuclear radioactive element A, they are produced at a constant rate alpha. It means the rate of formation of the nuclei A is given as alpha. Since this is a radioactive element, it also undergoes decay. Then what is the rate of decay? That rate of decay can be given by the lambda decay constant lambda and the number of elements that is given as Na. So then we can say that the rate of decay of A can be given as lambda into Na. Then what is the net rate of formation of nuclei A? So the net rate is given as dNA upon dt, that is what is the rate of formation alpha subtracted with what is the rate of decay lambda into Na. Now this is what we got as an equation, and with the help of this equation it is very easy for us to calculate what is the number of nuclei n for A at time t. Let me do small rearrangements. dNA upon lambda alpha minus lambda Na, that is equal to dt. If I integrate on both sides, at time t is equal to 0, the number of nuclei is n0. At time t, the number of nuclei is n. And we have to do some integration. Before doing integration, let us take this denominator alpha minus lambda Na as x. If I differentiate with respect to Na, then it will become minus lambda. Then we can write dNA is equal to minus 1 by lambda into dx. So if this is the case, then we can write integration of dNA can be written as minus 1 by lambda dx by, I have considered the alpha minus lambda Na as x, dx by x. So when you change everything in terms of x, then the limit also has to be changed with respect to x. Am I correct? Then we can write this n0 as alpha minus lambda n0, and instead of n, if you substitute here, then it will be alpha minus lambda n, which is equal to integration of dt, which is from 0 to t. Then we know that the integration of dx by x will be the natural logarithm of x, that is ln x. So minus 1 by lambda ln x, the limit is alpha lambda minus n0, alpha minus lambda n, and here it will be simply t. And if you substitute the upper and lower limit here, then it will become alpha minus lambda n minus ln alpha minus lambda n naught. Let me take the lambda that side, then that will be equal to minus lambda t. Then ln is equal to alpha minus lambda n and alpha minus lambda n naught. That can be written as minus lambda t. Then if you multiply with exponential on both sides, then it will become alpha minus lambda n by alpha minus lambda n naught, which is equal to e power minus lambda t. Let me take the denominator to the right hand side. Then it will become minus e power lambda t alpha minus lambda n naught. What we need is the number n for a nuclei A. Then let me take the lambda n that side. Then it will become alpha minus lambda n naught e power minus lambda t. then I can write n is equal to 1 by lambda alpha minus lambda n naught e power minus lambda t. So this is the n number of nuclei of A at a time t, and this is the answer for the question number A. Next we will try to find if alpha is equal to 2 n naught lambda, what would be the number of nuclei of A after one half-life? That is the question number B. It is given that if t is equal to the half-life capital T, that is one half-life, and if alpha is equal to 2 n naught lambda, then that time what will be the number of nuclei of A will be present. And we know that the half-life T is equal to ln2 upon lambda, and if we try to use this relation here, then n is equal to 1 by lambda alpha minus lambda n naught divided by, that's e power minus lambda t. Let me write like this, e power lambda, instead of t let me use the half-life. And we know that if I substitute ln2 by lambda here, then the lambda will get cancelled, remaining only ln2 will be there, then e power ln2 is simply 2. Then I can write n is equal to 1 by lambda alpha minus lambda n naught divided by 2. Then if we do further simplification, then alpha minus alpha by 2, it will be simply alpha by 2 minus into minus plus lambda n naught by 2. Then if we substitute alpha is equal to 2 n naught lambda, then it will become n is equal to 1 by lambda 2 n naught lambda by 2 plus lambda n naught by 2. Then here these two will get cancelled, or we can directly do the addition. Then 1 by lambda is equal to 3 n naught lambda by 2. Then lambda will get cancelled, then we can write n is equal to 3 n naught by 2. So what we found is, at the half-life, if alpha is given as this value, then the number of radioactive nuclei A is found to be 3 n naught by 2. And also they are asking us to find out what is the value, limiting value of n at t is equal to infinity, that is the maximum value. Now let us find out that one also by substituting t is equal to infinity and having the same value 2 n naught lambda in this equation, then it will be n is equal to 1 by lambda alpha minus, you see here, if I substitute t is equal to infinity, e power infinity is infinity, anything by infinity it will be equal to 0, the remaining term is simply alpha. Now if I substitute alpha is equal to 2 n naught lambda, then lambda will get cancelled, then n is equal to 2 n naught. This is the limiting value of n at t tends to infinity.